Hi, my name is dr. Ahmath. Welcome to the course of multivariable calculus. In this video, we're going to continue our discussions about the geometric series, and we are going to discuss the solutions to a couple of problems on that. First of all, I would like to remind you that the geometric series is given in this form, where we can expand this form by writing all the terms, where we need to just substitute n to be equal to 1, n to be equal to the 2, n to be equal to the 3, and so on to here. So if you substitute n to be equal to here, you're going to just get r in the power of 0, which is equal to the 1, and so that is why it's going to be simply a. Plus, so I need to substitute n to be equal to the 2 here. It's going to be r in the power of 1. It's going to be a r. Plus, now we need to substitute n to be equal to the 3 to here. It's going to be a r in the power of 2, and so on. So we call for any geometric series a as the first term, and r as the common ratio, or sometimes quotient. So the series, the sum, is if the sum is finite, some finite number, since we are adding infinite numbers together, right? So in some cases, the sum might be finite. If the sum is finite, then we say that the series is convergent. And this is possible when this general ratio, general quotient, is between -1 and 1, or if its absolute value is less than 1. And if r's absolute value is less than 1, the sum is going to be equal to the a divided to the 1 minus r simply. So otherwise, if r is not between -1 and 1, if r is even equal to 1, the sum is going to be infinite. In this case, we say that the series is divergent. So we are going to solve a couple of problems. The first problem is given like this: when n starts from 1 until infinity. So before we solve this, we need to bring this to the general or standard form of a geometric series. So when we say the standard form, I mean this form: a times r in the power of n minus 1. So I need to bring this to something with the n in something in the power of n minus 1. In order to do this, so let me write down the terms like this. So n starts from 1 to infinity. I would like to write as n in the power of 2 times n in the power of n minus 1, right? So according to the properties of the exponents, so if you have two numbers in the different powers, and if you multiply them, you need to just add their powers. If you add 2 to the n minus 1, you're going to get exactly n plus 1, right? So this is equal to this. I'm just rewriting this differently. So now I'm going to multiply this 5 in the power of 1 divided to the 5 in the power of 2n, right? So let me continue with this. So it's going to be the summation. N goes from 1 to infinity. So 9 times 3 in the power of n minus 1 times 5 times 1 over 25 in the power of n. So I would like to write down this 25 times n also differently. So here I can write this as 25 in the power of n minus 1 times 25, right? So in the power of 1. So in this case, they are going to be the same actually, right? So let me continue simplifying this. So now I'm going to take all the terms without the powers of the n together. It's going to be 9 times 5 divided to the 25 times, so 3 over 25 in the power of n minus 1, right? So this is going to be very much similar to the general form of a geometric series, right? Where this number is going to be a, and this number inside the brackets is going to be r. And if you remember, the condition for the geometric series to be convergent is that this r in the module should be less than 1. So the r is equal to the 3 over 25, and this is less than 1. So that is why the series is convergent, and its sum is equal to a divided to the 1 minus r. So the a is going to be equal to the 9 over 5, so 9 over 5. So divided to the 1 minus r, which is 3 over 25. So it's going to be 9 over 5, 22 over 25. So we can just cancel a couple of terms. It's going to be, if you cancel this and this, you're going to have 5, and this 5 goes up, and it's going to be 45 divided to the 22. So the sum of this infinite series is going to be equal to the 45 over 22. So now the interesting applications of the geometric series would be to write down this kind of numbers in a ratios. In a ratio form. So you probably have this kind of numbers, right? So this bracket means that you need to write this 17 infinitely many times, and so on. So what I want is, I would like to write down this number in a fraction, as a rational number. In order to do this, let me write down a couple of its terms in order to connect this with a series. So 2.317, 17, 17, and so on can be written as 2.3 plus 17 divided to the 1000, right? So it should be like a 0,000. So 10 in the power of 3, right? So if you divide 17 to the 1000, it's going to be 0.017. So if you add this to 2.3, you're going to get exactly this part. So plus 17 divided to, so now I need to represent this 17, right? It's going to be 17 divided to the 10 in the power of 5 to here. So plus 17 divided to the 10 in the power of 7, and so on, right? So the thing is, this part of this series is the geometric series. Geometric series, where a, the first term, is going to be equal to the 17 over 10 in the power of 3, for example, and the general quotient, the common ratio, is going to be equal to the 1 over 10 in the power of 2, right? So indeed, if you multiply r to the first term, you're going to get exactly the second term. If you multiply r to the second term, you're going to get the third term, and so on. So since r is less than 1, this part of the series is convergent, right? So its sum is a finite number, and we know how to evaluate its sum, right? So its sum is going to be equal to a divided to the 1 minus r. So we are going to write this as a, which is 17 divided to the 10 in the power of 3, divided to the 1 minus 1 over 100. So it's going to be equal to 17 divided to, so I'm going to cancel this 100 with this 1000. It's going to be 990, right? So 100 minus 1, it's going to be 99 times 10. It's going to be 990. So now I need to add this to the 2.3 actually. So this is going to be equal to 2.3 plus 17 divided to the 990. So I'm going to continue by writing down 23 as divided to the 10 plus 17 divided to the 990. I can give the common denominator. It's going to be 90 here. So if you multiply 23 to the 99, you're going to get 2,277 divided to the 990 plus 17 divided to the 990. If you add the 17 to this number, it's going to be 2,294 divided to the 990. So we wrote down this number with infinitely many terms in a ratio form. So let's go to the next interesting problem. So we are given this kind of series. We need to figure out whether the series is convergent or divergent. If this is convergent, let us try to find its sum. So this is very interesting series actually. So for the series, so let me write down a couple of terms. So if n is equal to 1, you need to substitute this. It's going to be 1 divided to the 1 multiplied to the 2. Plus, if n is equal to the 2, it's going to be 1 divided to the 2 times 3. If n is equal to the 3, it's going to be 1 divided to the 3 times 4, plus and so on. So I really like the series because it is possible to split the series into the two parts. Before we do this, let me define the partial sum. So the partial sum, if you remember, it was the sum of the first n terms of a series. It's going to be the summation So let me denote now the terms with the I goes from 1 to the n. So 1 divided to the I, 1 plus I, or I plus 1. It's going to be 1 divided to the 1 plus 2, plus 1 divided to the 2 plus 3, plus and so on, plus until 1 divided to the n plus 1. Right? So then the series, so if I would like to find its sum, what I have to do is I just need to find the limit of the partial sum when n goes to infinity. Right? So I'm going to simplify the partial sum actually. And the one interesting thing which I can see from here is that 1 divided to the 1 times 2 can be written as a 1 over 1 minus 1 over 2. Can you see this? So it's going to be 2 minus 1 divided to the 1 times 2. It's going to be 1 over 2. So at the same time, I can do this trick with the second term. So 1 divided to the 2 times 3 can be written as a 1 over 2 minus 1 over 3, right? Indeed, if you give the common denominators, they are going to be the same. So we can do this with the third term. So 1 divided to the 3 times 4 can be written as a 1 over 3 minus 1 over 4. So the thing is, I can do this with all of the terms. So 1 divided to the I times I plus 1 can be written as 1 divided to the I minus 1 divided to the I plus 1. If you give the common denominator, you get these two parts equal. So what I would like to do is, I would like to write down all the terms by expanding in this form. Right? The first term, the second term, and so on. So let me write this. So the summation of 1 divided to the I times I plus 1. So I goes from 1 to the n can be written as 1 divided to the 1.2, 1 times 2, plus 1 divided to the 2 times 3, plus and so on, plus 1 divided to the n times n plus 1. So let me write this. It's going to be a 1 over 1 minus 1 over 2. So this is the first term. The second term can be written as 1 over 2 minus 1 over 3, right? So the third term here is going to be written as 1 over 3 minus 1 over 4, then 1 over 4 minus 1 over 5, and so on, until 1 over n minus 1 over n plus 1. And do you see here that these two terms are going to be cancelled? These terms are going to be cancelled. And then these terms are going to be cancelled, these terms and these terms are going to be cancelled, and the only two terms which are left is going to be the first one and the last one. If you give the common denominator, it's going to be n plus 1 minus 1 divided to the n plus 1, which is going to be simply n divided to the n plus 1. Right? So the partial sum actually for the series is going to be simply equal to the n divided to the n plus 1. And if I would like to find out the sum of an infinite series, what I have to do is I need to find the limit of the partial sum when n goes to the infinity. It is going to be equal to 1. So this is also one of the interesting cases where we can find the sum of the infinite series using this kind of tricks. So in general, I would say that evaluating the sum of the infinite series is not so easy job. And if you are lucky enough, so it usually works for such a beautiful and good infinite series, like a geometric series, but in general it is a little bit more difficult job, and we need to try to learn more techniques in order to find the sum of the infinite series.